Heck, I've got a mouse. We're good. All right, so going over last night's homework, we were talking about roots and zeros. We learned the fundamental theorem of algebra, that the degree of our polynomial tells us exactly how many roots it has when it's set equal to 0. All right, so it tells us how many x-intercepts, so to speak, that it has, although some of them may be imaginary, right? So looking at last night's homework, what can I do to help you? Which problem should we take a look at?
Any of them.
Any of them. How about...
Yeah, right. All of them. That'd be cool.
Let's see. We'll start with 27. Let's see. I'm on the right page, right? Yeah. Okay. And then we'll look at one of the ones with the imaginary, because I merely had a chance to outline that yesterday. So I will make sure that we can do that one further. So let's see. So what is the directions? It says, given a function and one of its zeros, find all of the zeros of the function. So let's see. Let's set this up. So I'm going to make my table. And I will have 1, -4, 6, and -4. And they told us that 2 works, so I'm going to plug 2 in. Actually, I'll plug that in yellow. And we're going to synthetically divide by 2. All right? That will tell us 2 things. 1, it will give me the remainder of 0, verifying that it is, in fact, one of the zeros. Actually, I think I've had a multiple choice question in the past, like asking, like, what is a 0 of a polynomial function? And, like, one of the answers is, like, 0, like the number. It's not necessarily 0, right? Because it's any x-intercept. So zeros are not always 0. All right? We'll play on words there, almost. So let's see. Bring down the 1. 2 times 1 is 2, plus -4 is -2. 2 times -2 is -4, plus 6 is 2. 2 times 2 is 4, plus -4 is 0. Right, so that does indeed work out. Now, I do end up getting a depressed polynomial out of this, so I could choose to work further with just the depressed polynomial. All right, let's see, 1, -2, and 2. I don't think that one's going to have any real factors. I don't think.
Yeah,
Are they imaginary?
yeah. Which is why I got confused, because it's 0 was like a real number. It's a 2.
Right, let's see. So h of x would have... What is h of x here? What is my depressed polynomial? X squared minus 2x plus 2. And yeah, when I looked at this real quick, I realized that 1, that's not factorable, and 2, I don't think that it crosses the x-axis anywhere. So if I wanted to solve this, which we will, yeah, it looks like our little table would have failed on it, sadly. And today we'll kind of learn some techniques that will that will allow us to verify, right, that we wouldn't have had any other possible answers, but we would have had to solve it this way. So let's see. So let's solve that. So I guess I'll keep working in the blue. So we'll set that equal to 0. So x squared minus 2x plus 2 equals 0. And if I want to solve that, what strategy should I use? I already told you it's not factorable. What do you think? Right, that's our goal. And we've got 2 possible ways that would still work when doing that. Does anyone have an idea of what would one of those ways be? How could you solve a quadratic?
Isn't there that formula?
Yep, quadratic formula would work, in which a is 1, b is -2, and c is +2. So that's one method you could use. And that would also give you the imaginary answers. And then what's the other one that would work? Yeah, find the new c. That's completing the square. I'm going to do completing the square. Completing the square is my favorite way of doing these, especially when my b term is even, because then finding my new c term doesn't make things too ugly. So let's see. So to find my new c term, c is going to equal b divided by 2 all squared. So let's see. That's -1 squared, which is +1. So I'll add 1 there. Bless you.
Sorry.
No problem. And what should I do on this side of the equation? in this case, because it is on the opposite side of the equation, I can do the same thing. So I can add 1, just like balancing a scale. If I put the same amount of weight on both sides of a balanced scale, it'll stay balanced. And I didn't have to like multiply this 1 by anything because there was no number outside the parentheses or something that was manipulating it in some way. So it was just adding a regular old 1 to both sides. So let's see. So this left-hand side can factor to something like that, and the right-hand side is -1. What does the left-hand side factor to become? X minus 1 all squared. My favorite place to find that -1 is right here, the number I had before I squared it when finding my new c. But it's also going to always equal just half of your original b term. All right, so half of that. Well, I guess I have to be careful. Half of the b term of the thing that I'm factoring, right? So like, if I ended up having to like factor something out of it first, it's no longer the original b term. Now I'm just rambling. So let's see. Let's keep going. So now what do I do to solve for x?
You square
Root both sides, plus or minus. Don't forget it. There's that technique I was talking about. Technique. Let's see. So plus or minus square root of -1 is I, right? And then I can add 1 to both sides. And I get 2 answers that are both imaginary, and they are conjugates of one another, right? I've got 1 plus I and 1 minus I, which we talked about yesterday, right? If we have imaginary roots, not only do we have kind of like a quote-unquote positive one, but we also have an evil imaginary friend. So they always come in pairs, right? Yes.
So how do we know that this table doesn't work?
Well, we'll know that today. We'll know. So yeah. So you could have tried a bunch, and I appreciate your efforts in doing so. And I think also if you still tried a bunch of other ones, I think that the numbers you were getting would not have approached 0 like ever. I think they would have just been getting like further and further away, and you would have been like, I don't think this is getting back to the x-intercept anytime soon. It's heading off to infinity. So like you might have been able to read into that a little bit. But I don't expect that you guys would necessarily have that kind of intuition about a table all that much just yet. So I'm not speaking of that as if you were supposed to know that just yet. So
When you do use the table, do you know like which number to start with? Do you always start with the x and you?
Start with the what?
Like the 0 that they give you, like the 2.
Right, when possible. But today we're going to be given problems where they don't even give us a seed value, where we'll just be like, where do we start? And you're absolutely right. That is a concern because there's infinitely many numbers we could try, and we could spend a long time looking for ones that work. So you're right. That is an issue, and that's what the property we're learning today is going to help us narrow down. So let's look at another problem here. What did I do? 28 and 29? Anyone have a preference? Ooh. Yeah, 29 is a 4th degree, and it's got a placeholder. That one is interesante. Yeah, that would have been enough to mess us all up. Okay, so, all right, so I tried to outline this concept for us yesterday, so do not fret if you didn't quite understand this. But let's see, we know currently that we've got the following root. We know that 2i is a root. So if 2i is a root, what's another root we know about? Negative 2i, right? And in this case, that appears to be the opposite, but it's kind of like I had 0 plus 2i and 0 minus 2i, if you wanted to really think of those as conjugates. So I just want to point that out. That's why these appear to be opposites in this case, which technically they are opposites in this case, right? And how many roots do I expect to have? 4, right? So based off of the degree and the fundamental theorem of algebra and its corollary, I would expect that there are 4 roots altogether. Although they might be complex. Let's see. Now, could these remaining roots be complex? I mean, like imaginary? Could they?
Yeah.
They could? Why? Or what are your thoughts?
Well, there's 2 left, so if one was imaginary, it would have room for a pair.
Right? Yeah, so we know that imaginary roots come in pairs, so there's enough that we could have a pair of them, right? And like you also said, if one of them's imaginary, then I definitely know the next one is 2. All right, so that's a possibility. And also in terms of the shape of a 4th degree positive, right? If that's a W, that's an ugly W. That was almost like an 8th degree polynomial there. It's possible that its end behavior is just like pointing in the same direction both sides. Well, it definitely is doing that. And as a result, it's possible that it could just never cross the x-axis. All right, so these could both be imaginary. They also could both be real. All right, so we're not quite certain of that yet. But how are we going to find them? I'll show you. It turns out I can find a depressed polynomial that happens to contain the 2 roots that I know. Does anyone know how I could find that? What would the... Yeah, exactly, right? If those are the roots, or if these are x-intercepts, or if these are zeros, then that means factors must be x minus this, and x minus that. And if these are 2 factors that contain those 2 roots, then the polynomial I get when multiplying these factors is a depressed polynomial that contains exactly these 2 roots. And then the trick that we're going to do is once I have this depressed polynomial, I'll divide it into this guy, giving me another depressed polynomial that happens to contain the other 2 roots that I don't yet know. All right? So it's kind of like a little bit of a weird idea. So this depressed polynomial contains the 2 roots I do know, and I know that there's some other depressed polynomial that I don't yet know that will contain these other 2 roots. And the way I can find that is by dividing this into that. Okay? So general strategy, that's what we're doing. It takes a little while to adjust to, I understand. So let's multiply this out. This one's a lot easier multiplying out than the one we did yesterday. Let's see, so that's x minus 2i times x plus 2i, right, because the double negative. You could have simplified that right off the bat. I would trust you to do that. So let's double distribute this. X times x is x squared. X times 2i is Twix, is the way I read that. Then I've got negative Twix, right, when I multiply the middle 2. And negative 2i times positive 2i is negative 4i squared. So, what happens here when I simplify? Yeah, those Twixes kill each other, right? And what is I squared equal to? Negative 1. So negative 4 times negative 1 is positive 4. So this is just x squared plus 4, right? So that's my h of x. So I just found the depressed polynomial that contains these 2 roots. All right? So what that means is if I set this equal to 0 and solve, those would be my answers. All right? I just want to kind of build as many connections as I can. So now what we're going to do is divide x squared plus 0x plus 4 into my original polynomial, 4x to the 4th plus 0x cubed. I'm putting a placeholder even in my divisor. You technically could not do it and get away with it, but I might as well, be explicit there. 17x squared. Oh wait, there's 2 placeholders in this. Ay caramba. Wow, I didn't even spot the second one until just now. Man, this problem's full of holes. Now, if I had this problem written out this way and I had directions on a test that just said find the zeros of the polynomial, you could have just circled those and be like, bam, right there. Those are the zeros. Yeah. So let's try dividing this. I'm gonna, since we're a little bit familiar with long division, I'm gonna just kind of cruise through this. So 4x to the fourth divided by x squared, right? Leading term by leading term is going to be 4x squared. So I write that all the way over in my x squareds column here, right? Okay, so then multiply. I'll have 4x to the fourth plus 0x cubed plus 16x squared. Now I can subtract. These cancel. Those cancel if you want them to. I don't know what you want to think of 0 plus 0 or 0 minus 0. Cancels, I guess. And 17 minus 16 is 1x squared. Right? Then I can bring down the aux if I want to. So let's see, that was one full cycle of DMSB, so now I can divide again. X squared by x squared, just leading term by leading term. I get 1. So where should I write this 1?
Over the 4.
Yeah, over this 4 in the constants column. How nice. So multiply, 1 times x squared is x squared. 1 times aux is aux. Let's see. And 1 times 4 is 4. It looks like I would have needed to double bring down here, but that's fine. I kind of, yeah, it works out.
I didn't even put placeholders in my answer.
Yeah, sometimes you're lucky because this and this, or this and this happen to also be zeros. We never ended up getting those terms showing up. Whereas if in my multiplication, if I somehow ended up with a like a 2x cubed, you would have been like, oh no, where do I put my x cubed? Because you wouldn't have had an x cubes column. But coincidentally, yeah, you're right. That is an interesting point about this problem, that it turns out the cubes never show up in this problem, partially because of this and this. And the linear terms never show up, also because of those same reasons. So this one's kind of like an alternating every other degree represented. So let's see. And when I subtract these, what do I get?
0.
0. So what that tells me is that this is in fact a factor of my original polynomial, which is what we'd assumed, right? And what is another depressed polynomial? Let's see, I'll call it, I usually use h of x last. Oh well, I'll use g of x this time. So g of x is another depressed polynomial that contains my other 2 roots. Okay? So this one had 2 roots, this one had 2 roots, giving me the total, where did I go? 4 roots that I knew I was looking for. Okay? So now it's up to us what we want to do. I could technically try the synthetic division steps on this one and try a bunch of combinations. It turns out, sadly, they won't work. So the easiest way to do this is actually to set this equal to 0 and solve. I kind of always recommend setting it equal to 0 and solving anytime you have some sort of quadratic left, because we're masters at solving quadratics by this point, and it's more reliable than trying the other technique of that repeated synthetic substitution thing. Let's see, then I'd divide both sides by 4. You could have also, by the way, used the quadratic formula. You could have used completing the square, kind of. But in this case, because there's only one type of x to begin with, I just isolate that right off the bat. And I'll just root both sides, and it works out a lot easier. So x squared equals -1/4. And a root both sides, plus or minus, don't forget it. Bless you. And I think that plus or minus now is starting to make sense as to why my complex roots come in pairs, right? There's always a positive, kind of a negative version-ish, right? That works out. So I'll have plus or minus. What's the square root of -1? I. And what's the square root of 4? 2. All right. So it turns out those are my other 2 root. So it turns out this problem was just full of imaginary friends. All right. So, yeah, it appears as though at least these two problems from the homework didn't have a lot of that synthetic substitution table stuff showing up in it. So I apologize for that, but that is a strategy that I definitely wanted to show you yesterday. I don't know if the other one maybe was friendlier to it. What was the other problem we did? 28, was it? Yeah, the other one at least would have had a real answer. The answers to 28, by the way, were 2i, negative 2i, and positive 3, if you want to check your answer against that. All right. But we will use more of these tables today, so don't feel as though it was a lost cause, and your efforts in practice, even though it did not lead you to an answer that often last night, is still valuable in skill. All right? So let's see. All right, so this is all set for going over homework.